In this video, we're going to look at triangulated irregular networks. What we see on the right in this case as we try to understand or try to represent the surface of Mount Etna. And then once again over on the left is the raster or the digital elevation model. Geographers, we've been doing TIN models well before the recent geospatial revolution or the high growth of GIS in the past decade. And so the idea here is this is an older technique. But the reason why I'm talking about this or emphasizing TIN models is in the future, we're going to continue to see more and more of this particular data model in terms of representing the surface of not only Earth, but also even inside our living rooms, even inside our own personal spaces. And one of the things, though, it's also important to note, though, is there are some flaws or some disadvantages with this particular model, especially at the moment. We can see in this particular case and the map on the right, some of the interpolation, some of the guessing done by the GIS. Some of these areas are kind of made to look wonky and made to look kind of like they're angular features when in reality they're much smoother. But if you look at the peak here of this particular Mount Etna, you can say that if we zoom into this particular model, it does show it pretty well. How do I know that? Well, let's take a look at Mount Etna. And we can see Mount Etna has this triangular top that I think is very, very well represented with this particular model here that we can zoom in and see. And so we can see somewhat these angular features that are created. And now it's important to note that we see these colors here that help to accentuate or to show the triangular features here. Try to show kind of the shadow and some of the effect. And so we got some of the color techniques for helping to show off these irregularly spaced triangles. Now let's discuss a component of TINs known as nodes. And you can see these here on the map on the right. Those hollow yellow circles are the nodes. And so those are nodes or individual, think of them as points, that are the building blocks for the rest of these features that create the TIN. And so these points have an X and a Y, but of course also a Z. And so these nodes are the corners of the triangles. And by connecting these nodes with lines, especially in a 3D space, what it does is it creates these triangles. And we can kind of see how this creates, if we see on the map on the left, with some clever shading techniques, you can somewhat see these lines that create kind of this 3D perspective, and obviously this is a 2D surface. Also note that the nodes are farther apart in, let's say, the less complex or the flatter areas, the flatter surfaces. And once again over here is we have water, and so of course that's going to be shown with these nodes farther apart. Whereas when we get to more complex terrain, especially up here where the steep slopes really start to ramp up at the top of Mount Etna, or over here and we have the kind of this river valley through here, very complex. And so what happens is the nodes, what they do is they space them, and what they do is they try to space them where they're needed, essentially. And so they space them in more complex areas. You're going to see a ton of nodes. Less complex areas, you're going to see less nodes, which is very different than what we saw with the grid or the raster, where we had everything was equally spaced or regular based on those raster cells that we saw previously. And so these nodes, what happens is their irregularity can actually kind of be seen as an advantage. Essentially what it does is the GIS picks the best locations to put these nodes. And so it's kind of an efficient use of a computer and data. So when we think about, let's say, these nodes, where you're going to put them, you're going to put them where you're going to have, let's say, the peak of a mountain, or the floor or the bottom of a valley, or the edge of a cliff. And so fortunately, the computer does that for us, but these irregularly spaced, these kind of strategically placed nodes or points, especially when we think about using LiDAR, which of course, as you know by now, is a huge, massive data set, essentially we can be more efficient. We can take that LiDAR and then from there, efficiently pick the best nodes to create and best represent the surface. Another key component of the TINs, other than the nodes, are the edges. And so those edges are shown here as these individual lines that connect 2 points. So every single edge is connected by 2 points. So there's some topology, of course, involved. So we have a lot of data that can be stored. So we can, from this, we can see the slope of this particular line, because of course we have x, y, and z values for both of these nodes. And so from there we can say that we can identify the slope, we can identify the direction. And so you can kind of see how we can start to do bigger things than just kind of just look at an aerial or try to say, oh, that's a cool visualization. Now we can actually make calculations using these particular models. For example, if we wanted to know the slope along this particular line here, all we would have to do, because we know the x, y, and z, is just the old formula rise over run. The vertical distance divided by the horizontal distance separating the two locations. Boom, we just calculated the slope. And although I've already talked about these triangles, let's kind of go in and focus more on the triangles. Are kind of the final result of connecting all of these individual nodes with edges. Finally, the last component of the TINs, other than the nodes and the edges, is something I've already described, and that's the triangles themselves. And we'll use the term face, the triangular face, interchangeably here. So each of these triangular faces, what it's trying to do is it's trying to represent or trying to show the undulation of the surface below it. Once again, each of these nodes are the corners of the triangles have x, y, and z characteristics. And so because of that, once again, we can determine slope and aspect, or the direction of a particular triangle face. Further, we can also calculate volume. We can also kind of create a surface profile to try to understand the surface from a cross-section view. We can do a visibility analysis like we did in a previous exercise, so we can kind of say, well, what could I see from this particular location if I'm looking this way? So you can do view sheds analysis. And this is why engineers and transportation planners often use TIN models. What I did over here on the left is we have our TIN model, and over here on the right is each of those faces, it shows the slope. And so places that have the most severe slope are shown in yellow, or the steepest slope, let's say, and then the flatter areas are shown in blues and purples. And we can see very clearly that there, once you get close to the top of Mount Etna, the slope increases considerably. So let's zoom into this particular area. So here we see slope, and so we have a particular area here that's much flatter. Then you have steeper slopes, steeper faces over here, and that's of course there where the summit or the peak of the Mount Etna volcanic cone is located. So this is why what I call geographical engineers or civil engineers, transportation planners, and others, as I've mentioned in science-related careers, is now that, especially in smaller areas, they can calculate volume and discharge, and all kinds of creepy words like that, slope, aspect, flow, so they can go ahead and model or visualize landslides. And like I said, especially in these smaller areas, when you're modeling, let's say, the whole entire area of Mount Etna, and maybe it'd be a little bit more challenging. You'd have to really increase the points used. But in case of smaller specific study areas, this is where TIN models are becoming more and more advanced for those in science and math related occupations. Further, we can use TINs to show aspect, which is just essentially what direction is the slope facing. So we have over here, for the most part, we have yellow and green. So that means we have, logically, if we think about this being a cone, we have southeast facing and east facing slopes. Meanwhile, we go over here to the other side of Mount Etna, and we've got more north and northeast facing slopes. But of course, we have undulations and changes and differences throughout there. And so where would this be useful? Why would this become something that more and more people would use? If you have a solar panel, or you have an array of solar panels, you obviously want to have those suckers facing towards the southern horizon if you're in the northern hemisphere, and towards the northern horizon in the southern hemisphere. Because, of course, if you're facing towards the north, you ain't going to get much sun on that solar panel. So this is kind of a way in which, once again, of course, increasing the resolution, increasing the number of would be definitely what I would want to do if I was actually doing that. But nonetheless, this shows how we can take this information and apply it in the real world. We can see more of the kind of the dynamics of what's happening here. We have this particular summit is up there, and so we've got this particular triangle here. This particular faces to the southeast, whereas over here this one's facing somewhat to the northeast, over here to the north, and so we can see right through here is the summit, because we can see the change: west, northwest, over here south and southwest, and then we get to the more eastern facing slopes over here. What I did here was I just told the GIS to turn all of this particular tin, make it all green, make it all the same color, and what it does is it shows the hillshade kind of techniques here. You can kind of see the triangles are somewhat different shades of green. And this is often a good base map to use, kind of use this as a base map to kind of makes it kind of create kind of a little bit of a 3D view if you overlay on top of that your raster or your vector data. Finally, what I want to emphasize here in this particular image is how the triangular faces, the slope and the aspect along the face are uniform or are the same. So what we have, though, in terms of the points along the face, the elevation is, of course, where we're going to see differences. And so what I mean by that is inside this triangle, I clicked anywhere inside this triangle. I can click up there, over there, and what we see is the slope of this triangle is uniform throughout it. And so it's 21.24 degrees for both of them. Same goes for the aspect. And so this triangle, all points along this triangular plane or face are essentially the same slope and facing the same direction. However, as we can see here, the elevation is different. So we're going up the slope as we go from this node to that node.